Very good morning all of you. Welcome to the lecture number 49. In this lecture I am going to cover total two topics. The first topic is designing a counter which goes through random states instead of sequence like you have seen 0 to 7 or 0 to 15 or 0 to 10. These are all a sequence fashion. It is going in a sequential fashion. I am going to design a random counter which go in a random state like 0, 3, 5, 6 and goes to 0 or 0, 4, 6, 8, 0. So we are going to design a circuit which will show only these particular states and rest of states will not be shown. Okay, this is the first thing. And second thing is I am going to tell you most important problem. There is a lockout problem in the counters. Under what condition you are going to get the lockout problem and how to overcome this problem. These are the two content I am going to cover in this lecture. Let's start with the counter design which goes through a random states. So let's take example. Let us design a counter synchronous counter which goes through states 0, 3, 5, 6 and 0. That means it's going to count only total 0, 1, 2, 3, 4 states, and it will be in that loop forever as long as you have given clock signal to the particular circuit. Now we will follow as usual the same procedure. Step number 1. So if you want to count 0, 3, 5, 6, 0, if you want to represent these numbers in decimal form, you require minimum 3 flip-flops. Because 6 cannot be represented by 2 flip-flops, you require at least 110. That means minimum 3 flip-flops. Step number 2, you are supposed to write the state diagram. Since state diagram already defined, so you are supposed to start your flip-flop output 0 and it's supposed to goes to 3, then it should go to 5, then it should go to 6, then it should go to 0. This is a counting sequence. The rest all other combination I am considering as don't care for the timing. All other combination of states, all other combinations I am considering as a don't care. We will see why I am considering this condition later part. For the timing, assume that your counter will go only 0 to 3, 3 to 5 and 5 to 6, then 6 to 0. If you write in binary form, it goes from all zeros, then goes to 0, 1, 1, then goes to 1, 0, 1, then goes to 1, 1, 0 and goes to 0. So this is my state diagram. I am going to make the state table in step number 3. So step number 3, let's take the state table. So state table I am going to consider the present state, then next state. So I am going to consider Q0, Q1, Q2, Q0 star, Q1 star and Q2 star. So let's start with 0, 0. When it is 0, 0, next state will be 0, 1, 1. If the next state is 0, 1, 1, it's supposed to go to 1, 0, 1. If it is the 1, 0, 1 state, next state supposed to be 1, 1, 0 state. If the next state is 1, 1, 0 state, I am supposed to be all 0 states. Please remember, at this place I am not considering other combinations because I want to move my counter only these states, assuming that counter will not go to any other combinations. Ideal condition, your counter will not go to any other combination. Like if you look at here, there is missing 1, then 2, 3 is there, 4 is not there, 5 is there, 7 is not there. So these 4 combinations I am assuming that counter will not go to these states. I am assuming only these conditions. So this is my state table. Now step number 4, I am considering the T flip-flop for this circuit implementation for the simplicity. So in step number 5, I am going to make the excitation table by using T flip-flop excitation table. So that means I require 3 flip-flops, T0, T1 and T2. If you consider 0 to 1 transition requires 1, 1 to 1 transition requires 0, 1 to 0 transition requires 1, 0 to 0 transition requires 0. Similarly for Q1, 0 to 1 transition requires 1, 1 to 0 transition requires 1, 0 to 1 requires 1, and 1 to 0 requires 1. Similarly Q2, 0 to 0 requires 0, 0 to 1 requires 1, 0 to 1, and 1 to 1 requires 0, and 1 to 0 requires 1. So these are the required inputs for the flip-flop so that it will go to the desired counting state. Now we will see the step number 6, that is the minimization by using K-map method. So let's take for T0 first. So this is my Q2 bar, Q2, Q1 into Q0 bar, Q1 bar into Q0, Q1, Q0, Q1, Q0 bar. So if you start writing, this 0, 0 is related to 1, and next one will be 3 related to 0, that is 0, then 5 is related to 1, 101, 101, then 110, that means this is 0. So we have will 0th column, 3rd column, 4th, 5th column and 6th column. Rest all other columns I am considering as a don't care output. I am not going to care about those output whether those are 1 or 0. So if you simplify, my T0 going to be, if you take this entire thing as quad, it's going to be Q1 bar. If I take this as a quad, it's going to be Q1 bar. Similarly, if I take for T1, let's write for T1. Same thing, you are going to fill 0, that is 1, then 3, that is also 1, then 5, that is also 1, then 6, rest all are don't cares. So if you can take everything as octet. So my T1 is 1. Now let's take the T2. So if you take the T2, 0, 0 is 0, then 3 is 1, then 5 is 0, and 6 is 1, rest all are don't care. So in this case I can take this as a quad, so I can make a T2, as if you take this entire thing as quad, it's going to be Q1. So these are the required input you are supposed to give to the flip-flop so that your counter will go to the states which are defined. So these are the required input you are supposed to give to the T flip-flop so that your counter will goes to 0 to 3, 3 to 5, and 5 to 6, and 6 to 0. Now we'll try to construct the circuit in a moment. So we are having 3 flip-flops. This is my T0, the corresponding output is Q0, and second flip-flop, this output is Q1, and this is my T1, and you are having third flip-flop here, this is T2, and this output is Q2. The clock is given as usual, same for all the flip-flops at the same time. Now I am going to give my inputs. So if you look at here, T0 should be Q1 bar, that means I was supposed to take Q1 bar as an input here. This is my T0, this is Q1 bar, and T1 always 1, so that means you always connected to 1, and T2 is Q1, that means you are supposed to give this as input to the T2. Now this is my Q0, Q1 and Q2. Now we'll try to simulate the circuit by using a DIT software in a moment. So this is the circuit. If you look at here, we have taken 3 T flip-flops. J and K are shorted, make it T flip-flop, and second T flip-flop input is 1 always, and first flip-flop T input is Q1 bar. If you look at here, this is Q1 bar, and third flip-flop output is Q1 is connected as a third input to the third flip-flop, and this is my preset input, and this is my clear input, and clock is given at the same time to all the flip-flop. Now let's run the simulation. So first I made all the flip output to all the zeros. I'm going to make clear equals to 1. The moment I make clear equals to 1, the counter goes to 0 to 3 and 3 to 5 and 5 to 6 and 5 to 6 and 6 to 0. Let's see how it goes. 0, then 3, then 5, then 6, then 0. So the design counter is working according to our instruction or according to our predefined format. Okay. Now we have successfully verified the working of this circuit. It is counting from 0 to 3 and 3 to 5 and 5 to 6 and 6 to 0. So this is a standard sequence which we defined. Now coming to the problem which is going to encounter. Now coming to the lockout problem which is going to be encountered by this circuit. Suppose if output of my flip-flop goes to a state, either goes to a state which we missed during the design part. See, we clearly missed 1, then 2, then 4 and 7. So we missed these states of the flip-flop. Suppose due to any fluctuation in the circuit, if the flip-flop goes to any one of the state, either 001 state or 010 state or 100 state or all one state, whether it is going to count in the same sequence or not, or if it goes to in this state, whether it is going to come back to its original sequence or not, we need to test it. So if you assume, now let us consider the present state of outputs Q2, Q1 and Q0, and the respective inputs T2, T1, T0, and coming to the next state, that is your Q0 star, Q1 star and Q2 star. So this table will give you whenever your flip-flop outputs goes to invalid state. So let's see, when it goes to invalid state, what is the next state of your flip-flop, and with the next state of flip-flop where it goes. So let us assume the flip-flop is in 001 state, which is also invalid state as per our counting sequence is concerned. When it is 001, if you look at here, your T1 is always connected to 1, so this will be 1. Your T0 input is a Q1 bar. If you look at here, Q1 is 0, Q1 bar will be 1, and your T2 input is Q1 is 0. Now when T0 is 1, your Q0 will toggle, that becomes 0. When T1 is 1, your Q1 also will toggle, it becomes 1. When Q2 is 0, it will be in the same state. That means if the flip-flops in state 1, it goes to the number 2 state. Suppose if the flip-flop is in 010 state, in this case your T1 is always 1 because it is always connected to 1. Your T0 is Q1 bar, that means Q1 bar will be 0, and your T2 is Q1 is 1. So in this case, T0 0 means it will be in the same state. T1 is 1 means it will toggle, your 1 becomes 0. Your T2 is 1 means your Q2 will toggle, it becomes 1. That means going to the number 4. Suppose if it is in 4100, in this case again your T1 will be 1 as per the circuit is concerned, and your T0 will be again Q1 bar. Q1 bar is 1 bar will be 0 bar will be 1, and your T2 is Q1. Q1 is 0. Now if you write the next state based on this T inputs, T0 is 1, that means it toggle, that means it goes to 1, and T1 is 1, that means it also toggle, it will goes to 1, and T2 is 0, it will be in the same state. Now it goes to the number 7. Suppose if it is in 1 1, all ones, now your T1 is always 1, your T0 is Q1 bar. Q1 bar is 0, and your T2 is Q1. Q1 is 1. At this time your T0 is 0, that means it will be in the same state, that means 1, and your T1 is 1, that means toggle, your Q1 will toggle to 0, and similar T2 is 1, that means your Q2 will toggle, it becomes 0, that means it goes to 1 state. So you started with 1, so that means your counter will goes to 1, your counter goes to 1 to 2, then 2 to 4, and 4 to 7, and 7 to 1. This loop will be forever. So that means if the counter, if unknowingly or due to some fluctuation in the circuit, if the counter goes to any one of the state, either goes to 1 state or 2 or 4 or 7, it will be in the loop forever. Your circuit no more going to count 0, 3, 5, 6 sequence. It's not going to count this sequence. If the counter goes to one of the invalid output states, it will be in this loop 1, 2, 4, 7 loop forever. We'll test this observation by making all the flip-flop output to 7. We'll take the 7, so we'll make all the flip-flop output to 7. Then we'll see whether 7 goes to 1 and 1 goes to 2, 2 goes to 4 will happen or not, whether this will be in the loop forever or not by using a DEET software. We'll see in a moment. So let's take the same circuit once again. Now this time what I'm going to preset all the outputs to 1. Now if you look at here, your counter in a state which is not part of our counting sequence. Our counting sequence is 0, 3, 5, 6 and 0. Now we made all the flip-flop outputs to 7 to check whether the circuit will go back to the original sequence which we created, or it will be in the loop forever. Let's make it a run. Now you can check 7, 7 to 1, 1 to 2, 2 to 4 and 4 to 7, and again 7 to 1. So that means if the flip-flop goes to a state which is not valid, it will be in that loop forever. It is going 1, 2, 4, 7, again go back to 1. So this is what is meaning by lockout problem. So this is what is meant by lockout problem. Lockout problem is your counter or your flip-flop goes to a invalid state. Due to that invalid state, your counter count arbitrary numbers forever. So this is what is meant by lockout problem. So in our case, it's supposed to count 0, 3, 5, 6, 0, but it is going to the state 1, then 2, then 4, then 7, again back to 1. So it will be in this loop forever. So now your counter is facing a problem. That problem is called lockout problem. We'll try to see how to avoid this lockout problem by two solutions in a moment. Now coming to the solution to the lockout problem. First solution is you have to consider all possible states. You have to consider all possible states when you design counter. Suppose for example in our case 0 3 5 6 are valid output states. For this, next state is clearly defined. For 1 2 4 7, now we have to consider these output states also. For this next state we always define starting of your sequence. Or any other number in the sequence, or any other number in the sequence. So that means whenever your flip-flop goes to one of these invalid output states, your flip-flop output will either set to all zeros, that means nothing but 0 state, or 0 1 1 state, that's nothing but 3 state, or 1 0 1 state, or 5 state, or all ones, all or 1 1 0 state, that's nothing but 6. So whenever you flip-flop encounter one of these invalid output state, you are going to design a extra consideration so that your flip-flop output immediately goes to one of the state, depending on your how defined, whether you want to start it from all zeros, or you want to go to any arbitrary state which are valid. Once the counter is in this particular loop, it will again goes to the normal sequence. Like suppose if I set my invalid output states to, let's say 3, and next it will automatically goes to 5, then 6, then again goes to 0, again goes to 3. So that will be in the loop forever. That means it's going to count a valid counting sequence whatever we define. So if you define the next state for the invalid output states also, that means you are supposed to define next state for the invalid state. This is a one possible solution. We will see how it's going to work effectively. Second one is all undefined states or invalid states will be connected such a way that it going to reset all flip-flops to 0 0 state. So that means starting of your counting sequence. So these are the two possible solutions. We will first see by considering the all possible output states when designing the circuit. So we'll follow the solution number 1. Solution number 1 requires consideration of all possible output states and their next state also. You have to clearly define what is the next state also. Let's take the same example. 0 3 5 6 is your counting sequence. As usual, your step number 1 requires 3 flip-flops. Your step number 2, state diagram. Now I'm supposed to consider 0 to 3 and 3 to 5 and 5 to 6 and 6 to 0. Now I'm going to consider, if it is 1, it's supposed to be 0 0. Even if it goes to 2, it's supposed to come to 0 0 state. Even it goes to 4 also, it's supposed to come to 0 0. Similarly, if it's 7 also, it's supposed to go to the 0 0 state. That means whenever your flip-flop goes to either 1 or 2 or 4 or 7 state, in the next clock cycle it's supposed to go to all zeros, then it goes in the cycle forever. Or you can write it in this fashion. So your all zeros to 0 1 1, then 0 1 1 2, 1 0 1, 1 0 1 2, 1 1 0 and 1 1 0 2 0. Now you are supposed to take here 0 0 1 also will goes to 0 0 and 0 1 0 also should goes to 0 0 and 1 0 0 also will goes to 0 0 and all ones also should goes to 0 0. These are the 4 important consideration I am considering. That means we are defining if at all the counter goes to a invalid output state, in the next clock cycle it goes to all zeros. That means you are going to be taking your counter to the desired counting sequence so that it will be in this counter or counting sequence forever. Now let's take the step number 3, where we are going to make the state table. So in order to make the state table, you have to consider the present state, then next state. So first all zeros. So when it is 0, it goes to the zero 1 1, 0 2. If you look at from the state diagram, 0 2 3. Then suppose if at all encounter 1, it's supposed to go to all zeros. So please remember, this is important. This is an invalid output state. Whenever if it goes to invalid output state, it goes to all zeros. Then 0 1 0, this is also invalid output state. So again it's supposed to go to all zeros. Then 0 1 1, if it is 3, it goes to 5 state. Then if it is 4, it's supposed to go to all zeros because it's again invalid state. That's why we are making it all zeros. Then if it is 1 0 1, it's supposed to go to 1 1 0. If it is 1 1 0, it's supposed to go to all zeros. So 6 to 0. If it is 7, it's supposed to go to all zeros because this again invalid output state. If you observe carefully here, so this is one invalid state, 2 3 and 4 invalid state. For that you clearly define next state will be 0 0 0. Now I am going to consider the step number 4. Step number 4 I am considering again T flip-flop for the simplicity. And step number 5 I am going to consider write the excitation table, that is nothing but required T inputs for the given transitions T0, T1 and T2. Let's make it. So 0 to 1 require 1, 1 to 0 require 1, 0 to 0 require 0, 1 to 1 requires 0, 0 to 0 require 0, 1 to 0 require 1, 0 to 0 require 0, 1 to 0 require 1. So these are the required inputs for the T flip-flop to make the Q0 transition. Let's make it Q1 and Q2 also. If you look at the Q1, 0 to 1, 1, 0 to 0, 0, 1 to 0, 1, 1 to 0, 1, 0 to 0, 0, 0 to 1, 1, 1 to 0, 1, 1 to 0, 1. Look at the last one, 0 to 0, 0, 0 to 0, 0, 0 to 0, 0, and 0 to 1, 1, 1 to 0, 1, and 1 to 1 will be 0, 1 to 0 will be 1, and 1 to 0 will be 1. Now you got the required T input. Now we are supposed to make the T0 K map. So we will make it Q2 bar, Q2, Q1 into Q0, Q1 bar into Q0 bar, Q1 bar into Q0, Q1, Q0, Q1, Q0 bar. If you feel, it will be 1 1 0 0 0 1 0 1. Similarly, if you feel for T1, 1 0 1 1 0 1 1 1 So if you make the simplification, this will be one pair and this will be one pair. So your T0 will be Q2 bar times Q1 bar, plus if you look at this one, this is Q2 times Q0. Similarly, I can form so now let us form. This is one quad, this is one pair, and this one more pair here. So your T1 will becomes, so if you take this entire thing as a quad, you are going to get Q1 plus, if you take this as a pair, it's going to be Q2 into Q0. If you take this 2 as pair, it's going to be Q2 bar times Q0 bar. And similarly, if you write it for T2, so 0 0 1 1 0 1 1, so this is going to be one pair, and this one will be going to be one pair. So in this case your T2 will be Q1 Q0 plus, if you take this as a pair, Q2 times Q0 bar. So these are the inputs which we are supposed to give to the T flip-flop, so that your counter will be in the desired sequence of 0 3 5 6 again goes to 0. It will not go to the any invalid state or any invalid output state, or it will not encounter any lockout problem. We'll see whether this will work or not for our case. We'll design the circuit using the DEET software and we'll try to verify it. Now coming to the modified circuit of the previous circuit. Here my T0 is connected through two AND gates followed by an OR gate. If you look at the expressions, you require two AND gates followed with one OR gate. So this entire thing I am connected to T0. And similarly, if you look at the second T1 output, it requires total 3. If you look at the T1 requires 3 input OR gate followed by Q1 plus 2 AND gates. If you look at here, I consider the output from this AND gate. This is one AND gate, this is another AND gate, and third one I have directly taken. So total 3 inputs, and this output I have connected as an input to the second T flip-flop. And coming to the third T flip-flop output, you are going to have 2 AND gates followed with OR gate. If you look at the expression, 2 AND gates for these two boards, and there will be one OR gate. So this output OR gate is connected as an input to the third T flip-flop. Output of all the flip-flop connected to a 7 segment display, considering fourth bit as 0 always. Now if I run this circuit for the simulation, it is going to count only 0, then 3, then 5, then 6 and 0. Even if you introduce unwanted or invalid state as 7, still it is going to count in the same counting sequence. That we will verify in a moment. So let's clear it. So my counter is clear to 0. Now I'm going to make my clear equals to 1. The moment I make clear equals to 1, it's going to count 0, 3, 5, 6 and 0. Now you can see 0, then 3, then 5, then 6, then 0. Now I'm going to make my flip-flop outputs to all ones. Now all the flip-flop outputs are all ones. So that is nothing but 7. I intentionally made my flip-flop outputs to an invalid state. The moment I make my clear equals to 1, it's going to count as usual sequence what we defined. We'll check it now. 7 going to 0, then as usual 3, then 5, then 6, then 0. Even though we introduced an invalid state, still it is in the same counting sequence. In the previous case, when we did not follow when we did not consider all the possible output states, when you clear your flip-flop output to 7, when you run it, it's going to in the a arbitrary loop, that is 1 2 4 7 forever, which is not the desired sequence. So this is a lockout problem encoded in the circuit when you don't consider all the flip-flop output states. In the modified circuit, we have considered all the flip-flop states. Even if you take flip-flops into a undesired state, still it is going to count back in the normal counting sequence what we defined for the particular circuit. This is one way of avoiding the lockout problem. Now we'll see the second way of doing it in a moment. Now we are going to see the second solution for the lockout problem. Second solution for the lockout for the given example. So 0, 3, 5, 6 and 0 is our counting sequence. Invalid states are 1, 2, then 4 and 7. For this, if you write the equivalent binary form, this will be Q2, Q1, Q2 bar, Q1 bar, Q0, and 2 will be Q2 bar, Q1, Q0, 4 will be Q2, Q1 bar, Q0 bar, 7 will be Q2, Q1 and Q0. Now what I am going to do, I am going to add all these 4 minterms. If you look at this combination, so whenever 1 comes, 0 0 1 comes, this bit will be 1. Whenever 2 comes, this bit will be 1. Whenever 4 comes, this bit will be 1. Whenever 7 comes, this bit will be 1. So that means if you take this entire expression as a reset, circuit, so this circuit will produce output 1 whenever your flip-flop output goes to either 1 or 2 or 4 or 7 state. So this output of this reset circuit, I am going to give it to a, so this reset circuit output I am going to give it through a NOT gate to the clear input of my 3 flip-flops. So whenever one of this expression produces 1, that going to be complemented by your NOT gate to 0. This 0 will be applied to all the clear inputs of your flip-flop, so that your flip-flop output goes to the 0 0 state, which is a valid state. So if you simplify these 4 minterms, you are going to get Q1 XOR, Q2 XOR, Q1 XOR, Q0. So this is my reset signal. This entire thing I am going to connect it with a one NOT gate. There is nothing but over a bar we are going to write it here. That means your reset signal will be Q0, Q1, so through a XOR gate, and output of this will again go through a one more XOR gate, that is your Q2. This XOR gate output I am going to give it through a NOT gate. This is my reset signal. This I am going to connect it to the clear input of my flip-flops, so that whenever the flip-flop goes to one of the undesired or invalid state, goes to all 0 0 state. Now we'll try to check this circuit whether it will work for us or not. Now coming to the second solution, if you look at here, this is same as your first circuit. Only thing I made it here is I took an extra XOR gate for which I connected my Q0, Q1 and Q2 and followed by a NOT gate. Whenever this XOR gate output is 1, this output will be 1. Any one of the 4 invalid combinations are appeared. This 1 becomes 0 here. This 0 will be applied as a clear input to all the 4 flip-flop. As a result, it is going to count only a 0, then 3, then 5, then 6, again goes to 0. Let's run the simulation. Let's clear it. Now you can run 0, then 3, then 5, then 6, then 0. So this is how we can avoid the lockout problem by using the second method. Now we'll see the lockout problem in ring counters, how they are going to experience the lockout problem in a. Now let us consider the lockout problem in ring counter. Or shift register counter. If you remember your ring counter circuit, you are going to have 4 D flip-flops and clock is given simultaneous to all the flip-flops, and this is input to the next D flip-flop, this input next D flip-flop, this input next, and this will be come as a feedback to the first flip-flop. So this here D0, D1, D2 and D3. If you remember the procedure, you are supposed to manually set your D0 to 1 to start the counting process. This is the first thing. This will be done for a short period before the active clock pulse comes. Before the active clock pulse comes, so that it will be in 100 state before the next clock pulse comes. This will be D0, D1, D2 and D3. Next clock cycle will be 0 1 0 0 0 0 1 0, then 0 0 0 1, then it will be 1 0 0. These are the valid output states for the ring counter. Now let's say if at all the counter goes to any other state other than these states, what happens? So if the counter goes to any other state other than these states, what kind of consequence you are going to face? Let's take if the counter goes to all 0 states, so it will be circulated within itself. That means all zeros to all zeros forever. Similarly, all ones also, it will be circulated within itself to all ones again and again. So we'll verify this first, then we'll see the other possible combination of lockout. So this is my ring counter. Now what I'm going to do, I'm going to make all zeros first. And I'm going to make clear equals to 1. Now your circuit will be in all zeros forever, even though your zeros are circulating, but we cannot see because all are 0 0 state. If you look at your clock is changing with respect to clock, your all zeros are changing to all zeros, again all zeros and again all zeros, and goes on. It will be in this loop forever. That means if the ring counter goes to all 0 state, it will be in that state forever. Similarly, if I make all ones, and your circuit will be in the all 1 state forever. If you look at here, your 4 outputs are 1 1 1, and if you see your clock is changing, but still you cannot see any change in these outputs. That means your flip-flop outputs are in the same. That means all ones to all ones, all ones to all ones. So in case of a ring counter, your all ones and all zeros will going to produce a lockout problem. This is one possibility. We'll see the other possibilities in a moment. Now if you look at here, these are the other possible cases of lockout problem in case of ring counter. If you look at here, this we already seen, all zeros to all zeros, all ones to all ones. Similarly, if counter goes to 0 1 1, here 1 will be circulated, or 0 1 1, 0 0 1 1 also circulated, or 0 1 0 1 also will circulated within these two frames. Only this black color one is the valid counting sequence for the ring counter. So that means your ring counter may go into either this loop or this loop or this loop or this loop or this loop. We can definitely check this loop and this loop by using DIT software in a moment. We'll see these two loops, how the lockout problem will appear in case of a ring counter in a. Now let's run the simulation test the remaining two lockout problem sequences. Now if you look at here 0 0 1 1 0, now two ones are circulating and this will be in this loop forever. Your two ones will be circulated within these four flip-flops. It will never go to the original sequence which we defined for the ring counter. Similarly, if you make three ones, now three ones are there. If you look at here, the three ones are circulating without going to the original counting sequence state. So this is a problem we are going to face in case of ring counter whenever it goes to the invalid output state of the flip-flops. Now we'll try to see how to overcome this lockout problem in case of a ring counter in a. Now let us see the solution for the lockout problem in a ring counter. So to avoid the lockout problem, we are going to slightly modify the ring counter circuit so that it never goes to a lockout state, as well as it automatically starts. We don't have to give the manual one into the one of the first flip-flops what we did it in the previous. So in the modified circuit, this here D0, D1, D2 and D3. Now I'm going to connect my D2. This will be inputs as usual, serial in, serial out configuration. The serial out. What I'm going to do, I'm going to take the output of D1, D0 and D2 and connect through a NOR gate. And this NOR gate output I'm going to give as input to the first flip-flop. So with this modification, your ring counter automatically starts. First thing is, it is self-starting now. You don't have to self-starting counter. First thing, and second thing is, even if it goes to invalid state, it automatically comes back to original or required counting sequence. As usual, clock will be given to all the flip-flops. Now we will see this modified circuit in the DEET software, whether this modification, this extra NOR gate circuit will really start our counting sequence of ring counter directly without manual entry of one to the one of the flip-flops. And if you we will also try to see if you intentionally introduce an invalid state, whether it will be in the invalid state forever or it going to come back to the original counting sequence in a. So this is your modified circuit of ring counter. If you look at here, this time your preset is connected to common to all the four flip-flop and clear also connected common to all the flip-flop. In the previous design, preset was connected separate for the first flip-flop and rest three will be connected to preset once again, because we want to manually enter one into the first flip-flops. That's why we connected separate preset for the first flip-flop. Now we are not considering that point, because we are considering common preset for all the flip-flop and common clear to all the flip-flop. And I'm used one extra NOR gate here. If you look at here, your NOR gate input is your Q0, Q1 and Q2, and this output I'm giving as input to the first flip-flop. If I start this circuit simulation, it automatically goes to the ring counter sequence. Let's start. Let me clear it. So now you can see your ring counter sequence. Single one will be circulating in the four flip-flops. So if I make all ones for a moment, if I am going to take my counting sequence to an invalid state, now all ones, the moment I make all ones, moment I make my preset equals to 1, all ones automatically go back to the original counting sequence. Let's see. All ones is a invalid counting sequence. Previously, if all ones, it will be in the same loop forever. Now it's not going to be in the loop forever. It's going to come back to its original counting sequence. Let's see. Now you can see it's getting back to its original counting sequence state. Now you can see 0 0 1. Now 1 will be circulating. So that means even though you introduce a invalid state of all ones, still it is going back to its original counting sequence. That's why it is called self-starting and without any lockout problem. now if you look at here, this is the original ring counter sequence which is in black color. The counter goes to all one state. You can see here it's 112, 1110, then 110 and 001. It's going back to its original counting sequence. Similarly, if the counter go to any other invalid state, all zeros, again it goes to 001 state, or 101, again it goes back to its original counting sequence, or any other invalid output states. If the counter goes to any one of the invalid output state, after 2-3 cycles going back to its original counting sequence. That's how we can correct the lockout problem in the ring counters. So this is how we are going to design the circuits or counters or any sequence circuit which will not go to the invalid state forever. So for every circuit you have to check for the lockout problem. If there is any lockout problem, you have to add a extra additional circuit so that it will not go into the lockout state. So this is all for today's lecture. Thank you all.